This video covers the solutions to the tutorial problems associated with the "Why does your kettle boil" topic. Problem 1. This problem starts by asking us to convert temperatures from degrees Celsius into kelvins. Now, to convert from degrees Celsius into kelvins, we have to add 273.15. So first of all, we need to convert 27 degrees Celsius, and that is equal to 27 plus 273. No point in including the decimal points because we're not given any decimal points in this 27. So adding these two to get the temperature in kelvins gives us 300 kelvins. Next, we're asked to convert 100 degrees C. So 100 degrees C in kelvins is 100 plus 273, which gives us 373 kelvins. And finally, we're asked to convert 0 degrees Celsius into kelvins. So this is 0 plus 273, which is equal to 273 kelvins. In the next part of the question, we're asked to convert from kelvins to degrees C. So instead of adding, we now need to subtract 273.15. And so we've got 0 kelvins, and this is equal to 0 minus 273, which is equal to minus 273 degrees Celsius. So that's the coldest temperature that we can have. Next, we've got 100 kelvins, which is equal to 100 minus 273, which gives us minus 173 degrees Celsius. And finally, we've got 500 kelvins, which is equal to 500 minus 273, which gives us 227 degrees Celsius. Problem 2. In this problem, we're asked to explain how convection currents form in a room with a heater turned on. Okay, so here's our room. Here's the heater. Let's turn the heater on, so there's heat there. Now, what happens is that the temperature of the air around here increases. Now, we know that as the temperature increases, the volume of the air is going to increase as well, because objects increase in size as they are heated. And so that's going to mean that the air becomes less dense. So hot air is less dense, and so that causes it to rise. So as it is less dense, now as it rises, it comes into contact with cooler air around it, and so that causes the air to cool down. So as it rises, it cools, and so when it hits the roof, it's at equilibrium with the surrounding air, and so it's cooled down, and so it's more dense, and so it sinks back down to the ground. So cooler air sinks back down to the ground. And so then it gets to the heater again, and we get convection currents like this forming in the room. Problem 3. In this problem, we have a reservoir containing boiling water, and a reservoir containing an ice-water mix, and they're connected with an aluminium rod, and this has a length of 20 centimeters, a thermal conductivity of 238 watts per meter per Kelvin, and a cross-sectional area of 1.2 centimeters squared. And in the first part of the question, we're asked what is the temperature of each of the reservoirs and how do you know? Well, we know that the temperature of this reservoir is 100 degrees C because the water is boiling and water boils at 100 degrees C. We know that the temperature of this second reservoir is 0 degrees C because we have ice and water, and because they're touching, they must be in thermal equilibrium. So for ice and water to be in thermal equilibrium with each other, it must be at 0 degrees C. So 0 degrees C as water and ice are in thermal equilibrium. Now, part B of the question says, what is the rate of energy transfer along the rod? So the rate of energy, it'll be in the energy in the form of heat. So Q over T, which is the power transfer along the rod, is equal to Ka times the change in temperature along the rod over the length of the thickness of the rod. And so the thermal conductivity is 238. Now we need to times it by the surface area. So the surface area is 1.2, the cross-sectional area, it's 1.2 centimeters squared, but we want this in meters squared. Now in 1 meter, we've got 100 centimeters here and 100 centimeters here. And so 1 meter squared is equal to 100 squared centimeters squared, and so this is equal to 10 to the power of 4 centimeters squared. And so to get from the centimeters squared into meters squared, we need to times it by 10 to the minus 4. The inverse of this, we've got less meters squared than centimeters squared. Now the temperature difference between the two ends is 100 minus 0, so that's 100, and the length is 20 centimeters, which is 0.2 meters. And so solving this on the calculator, we get 14.28 watts, which to two significant figures is 14 watts. Now part C of the question says, how much ice melts in 1 hour? So we know that the energy added in 1 hour is the power times the time. So we've got the power is 14.28, and now we need the time, which is 1 hour. So there's 60 minutes in an hour and then 60 seconds. And so solving that, we have 51,408 joules added to the system. So how much ice is that amount of energy going to melt? We'll need to use our latent heat formula. Q is equal to mL, which tells us that the mass is equal to Q on L, which is the 51,408, and we're told that the latent heat of fusion is 3.33 times 10 to the 5. And so this tells us that the answer is 0.154 kilograms, which to two significant figures is 150 grams of ice melts. Problem 4. In this problem, we're asked how much heat do you need to add to increase the temperature of 500 grams, so the mass is equal to 0.500 kilograms of, first of all, water, and then for part B, we're going to do aluminium. And in the question, we're told that the change in temperature it goes from the initial temperature to the final temperature. The final temperature is 50 degrees C and the initial temperature is 10 degrees C, so it's a change of 40 degrees C. And we know that for water, CW is equal to 4186, and for aluminium, the specific heat of aluminium is equal to 900. And the units for this are joules per kilogram per Kelvin. Joules per kilogram per Kelvin. And so we've got Q is equal to mCW delta T, and our mass is 0.500. This is 4186, the specific heat of water, times the change in temperature, which was 40. And so solving this on the calculator, we end up with 83,720 joules. And so we'll give this to two significant figures because these temperatures were to two significant figures. So this is 84 kilojoules. Or you could put 84,000 joules. So for aluminium, same formula. Q is equal to mc delta T. And so this is equal to 0.500 times 900 times 40. And so this is equal to 18,000 joules, which we can write as 18 kilojoules. Problem 5. So in this problem, we're asked how much energy is required to melt a 30 gram ice block. And we're told that the latent heat of fusion of the ice is 3.33 times 10 to the 5 joules per kilogram. So in order to work out the energy required to melt the ice, we can use Q is equal to ml. The mass of the ice is 30 grams, so this is 30 times 10 to the minus 3 kilograms times the latent heat of fusion, which is 3.33 times 10 to the 5 joules per kilogram. So solving this on the calculator, we get 9,990 joules, which we should give our answer to two significant figures, as the 30 grams is given to two significant figures. So this is equal to 10,000 joules. Now the question goes on, if this ice block was placed in a 200 milliliter glass of water, okay, so let's draw that. Here's our glass of water, here's our ice block, and this is 200 milliliters, which remember is equal to 200 grams of water. And we're told that the initial temperature of the water is 27 degrees C, and we're told after the ice is melted, what is the temperature of the water, and we're told that we can assume that there's no energy exchange between the surroundings. So that tells us that the total energy change is equal to 0. And so 0 is equal to the energy given to the ice to melt it. Now once the ice is melted, it's then melted ice at 0 degrees C, and so it needs more energy to raise its temperature up to whatever the final temperature is. So that amount of energy is equal to the final temperature minus the initial temperature of the ice, which will be 0 degrees C. So this term here, combined, is equal to the energy gained by the ice, and that energy is lost by the water. So the water loses energy as its temperature decreases, and so the amount of energy lost by the water is given by the mass of the water times the specific heat of water times the change in temperature of the water, which is the final temperature minus the initial temperature of the water. So now what we can do is we can substitute in. We know that ml is 9,990 joules. We'll keep all the significant figures for the working and then present our final answer just to two significant figures. Plus we've got 30 grams of ice times, once it's melted, it's water, so this is 4,186, times the final temperature minus the initial temperature, which is 0, plus the mass of the water, which is 0.200 kilograms because it's 200 grams, times 4,186 times the final temperature, which we're trying to find, minus the initial temperature. Now, in order to solve this, what we're going to do is we're going to move all the numerical terms over to the left-hand side and leave the terms with a TF on the right-hand side. So we'll move this one over, so we've got minus 9990, and now 0.2 times 4186 times minus 27 gives us minus 22,604. So we move it over to the other side, it becomes a plus. 22,604 is equal to, and then we've got our terms with a TF in them. So 30 times 10 to the minus 3 times 4186 plus 0.200 times 4186, or times TF. And so we can rearrange this. TF is equal to this side, which is 12,614 over the term in this brackets, which when you put it into the calculator, you get 962.78. So solving this on the calculator, we get 13.1 degrees C, but we should give our answer to two significant figures, so that's 13 degrees C. Problem 6. So in this problem, we're told to assume that sweat has the same thermal properties as water, and that on a hot day, we sweat 500 milliliters in an hour. So the mass sweated in an hour is 500 grams, and so the time is 1 hour. And we're asked, how much energy do you lose? So to work out this, we'll need to use the latent heat of vaporization. So we use the formula that the heat lost is equal to mL. So this is the mass in kilograms, so that's 0.500 times the latent heat of vaporization for water, which we're assuming is the same as sweat. So that's 2.26 times 10 to the 6 joules per kilogram, and this is in kilograms. So when we multiply these two together, we end up with 1,130,000 joules. So let's write that as 1,130 kilojoules. In part B of the question, we're asked what is the rate of energy loss or power due to the evaporation of sweat. So the rate of energy lost, the power, is equal to energy over time, which energy is in the form of heat in this case, so it's Q over T. So this is 1,130,000 over the time. Now the time is 1 hour, but to get the power in watts, we need the time in seconds. So in an hour, there is 60 minutes and then 60 seconds. So we divide by 60 twice. And so doing this on the calculator, we end up with 314 watts. And that is power which is lost by us because on a hot day, we're trying to lose energy. Problem 7. So in this problem, we're told that your kettle requires 1,500 watts to run. So we've got that the power is 1,500 watts. You fill it with 1 litre of water. So the mass of water is 1.0 kilograms. And the initial temperature is 21 degrees C. And we're asked, how long does it take your kettle to boil? So we'll need to make use of a couple of equations to answer this. We know that the power used is equal to the energy over the time, so energy in the form of heat in this case. So we can rearrange this to put Q is equal to PT. Now we know that that heat goes into changing the temperature of the water. So for heating water, we know that Q is equal to mc times the change in the temperature. So we can now use this equation to work out the time. So the lowercase t stands for the time, the capital case T stands for the change in temperature here. So the time is equal to mc times the change in temperature over the power. Okay, so now we know what all these things are, so we can substitute in. So we've got that the mass of water is 1 kilogram, the heat capacity of water is 4,186 joules per kilogram per Kelvin. The change in temperature, the final temperature is 100 degrees C if it's going to be boiling, and the initial temperature is 21 degrees C, and the power used by the kettle is 1,500 watts. So that's a relatively low power for a kettle, so a slowish kettle. And so solving this on the calculator, you end up with 220 seconds. So that's one way to answer it. Alternatively, we could convert this into minutes. Now, 3 times 60 is equal to 180 seconds, and 4 times 60 is equal to 240 seconds. So it's not quite 4 minutes, so it's something above 3 minutes. So this tells us that it's 3 minutes. And then to get the number of seconds, we'll have to subtract 180 from 220, and that leaves 40 seconds. So we could write this as 3 minutes and 40 seconds if we wanted to, or we can just leave it as the 220 seconds. Problem 8. This problem says explain why the desert, where you are surrounded by sand with a heat capacity of 830 joules per kilogram per Kelvin, has much greater temperature fluctuations between night and day than coastal locations. Okay, so to explain this, we're going to have to make use of the formula Q is equal to mc delta T, where this is the change in temperature. Now Q, this is the heat which comes from the sun, so we can assume that this is constant between the coast and desert. So that's just because this heat comes from the solar radiation, and we would expect the same amount of solar radiation to be hitting the desert as the sea. It shouldn't depend where on the surface of the earth you are to a certain extent. And so the seas, the specific heats are different. C for the desert, for the sand which makes up the desert, is 830 joules per kilogram per Kelvin, while for water in the coastal regions it's more like 4,186. So this is much smaller in the desert, and so that tells us that the change in temperature is larger in the desert. So that tells us that the temperature fluctuations between night and day will be much larger in the desert, as the specific heat of the sand making up the desert is much smaller. And problem 9. Explain why you stir a hot saucepan with a wooden spoon rather than a metal spoon. Include an equation in your explanation. Okay, so here's your saucepan and here's your spoon. Now, what we care about is the transfer of heat along this spoon, because this is what's going to burn your hand. So the transfer of heat, P, is equal to Q over T, which is equal to Ka times the change in temperature over the length of the spoon. So this is your delta X here, which is the same for the wooden spoon or the metal spoon. A is your cross-sectional area, which will be the same for the wooden spoon or the metal spoon. The change in temperature will be the difference in temperature between this end, the hot liquid, and this end, so the air. And so what's different between the wood and the metal is this thermal conductivity constant here. So K for wood is much lower, which tells you that less heat is transmitted to your hand, which implies you are less likely to burn your hand. So that is why you use a wooden spoon to stir the hot saucepan instead of a metal one. This is problem 10. So in this problem, we're told that we've got the temperature time graph, and we need to use it to work out how much power the kettle supplies. So we're told that the volume of water is 2 litres, which tells us that the mass of the water in the kettle is 2 kilograms. And we're going to need to use a couple of equations. We're going to need to use that power is equal to energy over the time, and energy in this case is in the form of heat, so Q on T. And we also know that heat is related to the change in temperature through mCW times the change in temperature. So combining these two, we've got that power is equal to mCW times the change in temperature over time. So using our graph, we know that the gradient of the graph is equal to the rise of the graph over the run Now, the rise is equal to the change in temperature. That's what we've got along the y-axis. And we've got the change in time, or the length of time, along the x-axis. So let's measure those as accurately as we can. Let's draw a vertical line up from 200 seconds to this point here. And then to get the temperature at 200 seconds, we'll draw a horizontal line across to here. So we've got that's at 62 degrees C there. So the change in temperature, we're going up from 20 to 62. So that's the final temperature 62 minus the initial temperature 20 over the change in time. The final time's 200 seconds and the initial time is 0. So that's our change in temperature over time. Now, rearranging this equation here, we can see that the change in temperature over time, we've got to divide this by mCW. So this is equal to P over mCW. And so we can say this is equal to P over mCW. So what the question's asked us to find is this P. So let's rearrange this part of the equation to find out what P is. So P is equal to mCW times 62 minus 20, so that's 42, over 200 minus 0, so that's 200. So substituting in, the mass of water is 2 kilograms, so this is 2.0. The heat capacity of water, we're told, is 4,186 times 42 over 200. So solving this on the calculator, we get 1,758 watts. But we were only given the volume to 2 significant figures, so we should give our answer to 2 significant figures. So that's 1,800 watts.